All right, today we're going to talk about eigenvalues and eigenvectors. So we're going to start with kind of what are they, and then we're going to move into how do you know if you have one. So to start out without kind of, we're going to do a little bit of a discovery on what is an eigenvalue, what's an eigenvector. So let's take this linear transformation. So this is just a transformation matrix, and it's a little hard to see, but there is our E1, which is here. So remember, E1 is your standard unit vector, and E1 is 1, 0, and E2 is 0, 1. So let me erase this. So E1 starts where the blue dot is over here, because it's at 1, 0. And we have 0, 1, which is our second standard unit vector. And if you notice, kind of what it does is it's a bit of a rotation, but it could also be a stretch depending. So the y component is being moved, but at the same time, you notice when we have 1, 0, it gets put to over here. So it does kind of a rotation along with an extension of it. Versus when we just looked at 0, 1, all it did was it took 0, 1 and made it 1, 0. So it kind of changes around. It changes your x component. Sorry, it changes the y component to be like an x component in this one. But let's take two very specific vectors. Now, if you're wondering, why'd you pick these two vectors? It's specifically for this example. There aren't any other vectors that will work in this case, and I'll get to why that is later on. So if we were to multiply this, we get negative 3 halves times 2, which would be negative 3, plus negative 1 times negative 3, or negative 1 times 1, which would be negative 1. Add those two together, and we get negative 4, because remember you do this times this. So negative 3 halves times 2 plus 1 times negative 1, and then we do 1 times 2 plus 0 times negative 1. So we get negative 4, 2. Now, notice here, you could factor out a 2. But specifically, if I factor out a negative 2, then lo and behold, I get back the original vector that I had. Now let's try this with the second vector in the same transformation. Notice the transformation matrix is not changing here. So negative 3 halves times 1 is negative 3 halves plus, 2. So negative 3 over 2 plus 4 over 2 is going to be 1 over 2. And then, 1 times 1 is 1 plus 0 times 2. So we just get back 1. Now, in this case, if I factor out a half, that just makes this 1. But what do I need to multiply by a half to get 1? I need to multiply 2. So in this case, I also get back the same thing. So, and what you can see is for the red one, which is our 1 half, or sorry, not 1 half, 1, 2, it kind of just scaled it down. And then if you look at 2, negative 1, it changed its direction and also extended it. So what ended up happening is we applied the transformation to a vector, and the transformation was just actually multiplying a scalar times that same vector. Notice though, when we did that with our standard unit vectors, that didn't happen. They actually had a bit more extreme of a change. They rotated a little bit differently. They stretched in some components, but they would either rotate or just kind of stretch or get moved around, but it wasn't to a perfect scalar. So that leads us into what's an eigenvalue and what's an eigenvector. So an eigenvector of a matrix A, which is an n by n, very key here, we have to use square matrices, is any vector, not the zero vector, such that A times u equals lambda times u for some scalar lambda. That means specifically there's a matrix that when multiplied by the vector yields the same result as just a constant multiplied by the vector. And we use the Greek letter lambda to represent that. So for our example, we had 2, -1, and 1, 2. So 2, -1, and 1, 2. Those were the eigenvectors. So the scalar lambda is the eigenvalue, which if we go back again, notice that the first vector was -2 times the starting vector, and then we had 1/2 times the second vector. So the corresponding eigenvector or eigenvalues are -2 and 1/2. Because when I did this first vector times A, it was the same as if I had just done -2 times the vector. And then similarly for the second vector and the second eigenvalue. So we have eigenvalues are a number, and of course an eigenvector is a vector. So there's a lemma that says if A is a square matrix and 0, which is not equal to u, is in the null space, then u is an eigenvector of A associated with the eigenvalue 0. That kind of makes sense though. If you look at it, so think about it, remember, if it's in the null space, that means if you multiply it by A, you're going to get 0. So, of course, you can have an eigenvalue of 0. But the thing is, eigenvalues of 0 are kind of boring. So, typically, they do exist. They are useful. However, they may not be the most interesting thing in the world. So, just to look at the book definition, again, eigenvector of an n by n matrix is a non-zero vector x, specifically the non-zero part, such that for some scalar lambda, a scalar lambda is called an eigenvalue, blah, 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 and it has a corresponding value. Pretty much the same thing we said here, just a little bit more formalized. This is where it's going to be a little bit more useful. Lambda is an eigenvalue of an n by n matrix A if and only if this equation, A minus lambda I times the vector x, has a non-trivial solution. Remember, the trivial solution is just 0. And if you notice from up here, we have ax equals lambda x. So then if I do ax, if I subtract lambda x from both sides, I get this. And then using the previous idea, or then using the idea of factoring out this vector x, you wind up with a minus lambda I. Notice it's not just a minus lambda, because lambda has to be multiplied by something. Because if we're going to put these two things together, they have to be the same dimension. You can't add a 4 by 3 to a 3 by 4. The components don't match up. So this is going to be a minus lambda I times x equals 0. So this is the way that we're going to try and figure out what goes where with this. So previously, so if you notice with the previous ones, I gave you a vector and then we multiplied it and we said, oh, cool. We could factor out a value and get back the same vector. We don't want to do that all the time because the guessing and checking part might not always happen. Or I shouldn't say might not always happen, but it might not be as easy. So the set of all solutions of 1 is the null space of this. Because remember, the null space is just what are all the values of x that when I do the matrix times x, I get 0. So I've got a very specific null space that deals with eigenvectors and eigenvalues. So that set is a subspace of Rn, and we call that the eigenspace of A that corresponds to lambda. So if you change up A and lambda, you get different eigenspaces. The eigenspace, of course, will consist of the 0 vector and all the eigenvectors corresponding to lambda. So, and again, this is why I say it's kind of like you want to throw out the trivial solution. If you have 0, 0, 0, of course that's going to work with something times x equals 0. If you just multiply everything by 0, you get 0. So we kind of tend to focus on what are the non-zero vectors. So like for this one, let's show that 7 is an eigenvalue of the following matrix. And then once we have that, let's find the eigenvectors associated with it. So the scalar 7 is an eigenvalue if and only if this equation has a non-trivial solution. So our A was 1652. So what I'm going to say is, does 1652 times x equal 7 times x? And so remember we said, well, what if I subtract it over? So then I get 1652, I'm going to throw this in parentheses, minus, if the computer will let me write, 7 times the identity matrix times x, and that equals 0. So now, if you notice, I have a vector, or I have a matrix that I can deal with. So you would distribute the negative 7 in. And so this would be, if I add the two matrices together, I would get negative 6 and 6. And then 5 wouldn't change. And then I would get negative 5 times x equals 0. So what I'm looking at now is what values of x that such that when I multiply them by 0, I get, or such that when I multiply the matrix times x, I get 0. So this is the same as finding, so remember this is A minus lambda I, not lambda imaginary, I being the identity matrix. So now I need to find what is null, or the null space of A minus lambda I. And to do that, I need to figure out where does negative 6, 6, and then it becomes an augmented matrix. Where does that, or what are the vectors that make this true? So I'm going to divide the first row by, I'm going to pick negative 6 just because, you know, make it a little bit easier. So this is going to become 1, negative 1, 0. And then I could multiply the row by negative 5, add it to the second row, and I would get 0, 0, 0. So now I actually have that this has a non-trivial solution, because notice we've got a free variable. And remember, free variable means non-trivial solution. So what I've got now is that if I were to set this up as a matrix, I have x1 minus x2 equals 0. So then that means that x1 has to equal x2. And of course, x2 would equal x2 because it's a free variable. So your vector x is going to be just the vector 1, 1. So this is your eigenvector. And we got the eigenvector from finding the from doing the original matrix minus the eigenvalue times the identity matrix. And you notice if we wanted to check this, if I did, I'll write this down here. If I do -6, 6, and 5, -5, multiply that by 1, 1, then I do get 0, 0. Now, this is where you have to be careful, because if you remember, the null space is the set of all linear combinations of that vector. So 1, 1 would work, 2, 2, 3, 3, half, half. Those would all work. But because we don't want to introduce another constant, we just take the base eigenvector without any scalar multiplied by it. So our eigenvector is just 1, 1. You wouldn't say 2, 2, or 3, 3, or 4, 4. You take it in its simplest form, which is, if you were to put it in the null space, it would be, or as the span, it would be 1, 1 times a constant. But we don't need the constant. We just want to take the, pardon me, we just want to take the base eigenvector. And so to test and see if this is true, I'm going to do, so that was the process to find the eigenvector, knowing the eigenvalue. So then just to double check, if I do 1, 6, 5, 2, and multiply it by 1, 1, then I get 1 times 1 plus 6 times 1, which is 7. And I get 5 times 1 plus 2 times 1, which is also 7. And we could factor out 7 and get 1, 1. So this is the eigenvalue. And this is the, what you say, associated eigenvector. Because if you have multiple eigenvalues, you don't just say, I have an eigenvalue and I have eigenvalues and eigenvectors. You can say that, but if you want to be specific, you say, this is the eigenvector associated with the eigenvalue, blah. So you make sure that you always want to specify those. So let's expand it to a 3 by 3. So this matrix has an eigenvalue of 2, and we need to find a basis for the corresponding eigenspace. So if our eigenvalue is 2, we'll start there. I like to give myself enough room. So to skip a couple steps, because remember we're going to have basically ax equals 2x. So this is going to be minus 2, 2, 2, 0, 0, 0, 0, 0, blah. Just like that. So next thing I'm going to do is just put the two together. And I'm going to get Well, again, these are minus, so this is going to be 2, negative 1, 6, 2, negative 1, 6, and 2, negative 1, and you guessed it, 6. So in this case, we have quite an extreme case. Because remember, then I'm going to set it equal to 0. So this is actually probably one of the easiest matrices that you'll ever get to row reduce. Because all I've got to do is add negative row 1 to both row 2 and 3. So that's going to give me 2, negative 1, 6, 0, and then all other entries are just, well, 0. So in this case, we actually have not 1, but 2 free variables. And I'm going to go ahead and divide this by 2 just to make it a little bit easier. So this will be 1, negative a half, 3, 0, and again, all these entries are just 0. So if I set this up, I'm going to get that x1 minus 1/2 x2 plus 3x3 equals 0. And then again, x2 will be x2 because it's a free variable, and x3 will be x3 because it's a three variable. It's a free variable. Let me speak correctly. So that means that we have x1, x2, x3 will be equal to negative 1/2 x2, or positive 1/2 x2, minus 3x3. And then you can think about this as x2. And you can think about, go back. You can think about this as being plus 0x3. And then you can think about this one as being 0x2 plus x3, which translates into vectors as x2 times 1/2, 1, 0, plus x3 times negative 3, 0, and 1. So we actually have 2 eigenvectors in this case. They are 1/2, 1, and 0, and negative 3, 0, 1. So this is the basis for the eigenspace, are these 2 vectors. Because remember, the eigenspace is just the null space for what we ended up doing, which was I didn't even do that right. I said A and wrote 2. So this would be ax minus 2x equals 0, which would then become a minus 2I times x equals 0. So these are eigenvectors and the basis for the eigenspace. And again, I keep saying that a lot. So if you were to just do the null space for this, it would be just the 2 vectors, 1/2, 1, 0, and negative 3, 0, 1. And then you would say any linear combination of those 2 is also in the null space, which is true. However, in this case, you have to keep in mind that all you want is just what are the vectors that are associated. You don't need a linear combination of them. You don't need a scalar multiple added to scalar multiple times the first plus another scalar multiple times the second. You just need the two vectors in their simplest form, because that is the core component of this. You just got to think about it as, I just need that particular vector because that vector will tell me what the scalar is. Well, I should rephrase that. If I use that eigenvector, I will discover an eigenvalue. And if you notice for these two, I gave you, or we were given the eigenvalue, and we needed to find the eigenvector, or in this case, vectors. You're not always going to be given the eigenvalue, which we'll cover how do you find it in that case without having, or we'll cover later, how do you find it without having to just do a guess and check method the whole time. Because you can do that, but you could be sitting there forever. So if you take a look at this one, the eigenspace that's shown in the following figure is a two-dimensional subspace of R3. So what it does is it takes anything that's on that plane, and it's either going to, or it's, if you multiply it by A, it's going to basically just stretch it. So again, our eigenspace, remember we said it was any linear combination. So it means any linear combination of those vectors are going to be basically stretched by a value of 2. So your eigenvectors form that eigenspace, and the eigenspace means multiplication by a transformation matrix is the exact same as just multiplying by the scalar, which in this case is 2. So when you find the eigenspace, you have found this space of vectors such that a linear transformation is the exact same as a scalar multiplication. It's a very specific plane on this graph, or in this space. So it's very interesting to see geometrically what's going on here. Because with the other ones, if you thought about it, what ended up happening was, like, go back to the very first problem. It would either switch, or it switched the x and y component for the y value, but then it would play a different game with the x component. So those would not stay on that same plane. You notice with these, it's kind of like we talked about with the subspaces. They don't leave this particular plane. The eigenspace it'll be stretched by a factor of 2, or dilated, if you want to be a little bit more mathematical about it. So the eigenspace is a plane in your original space where the linear transformation acts like scalar multiplication. And again, it's associated with a specific eigenvalue. So again, if you go back here, we had 1/2, 1, 0. If you wanted to make it a little bit easier, you could say 1, 2, 0. Again, that's for using a basis of the eigenspace. When you're using eigenvectors and eigenvalues, leave it as the original vectors. And then a couple theorems. The eigenvalue of a triangular matrix are just the entries on its main diagonal. So if you have basically an echelon form matrix, the eigenvalues are just what are the entries. So for 1, 3, -7, and then this can be, really screw this one up. It has the eigenvalues of 1, 3, and -7. It's just pretty easy like that. And then theorem 2 says that if v1 and v through vr are eigenvectors that correspond to the distinct eigenvalues lambda 1 through lambda r of not matrix A, then the set of those eigenvectors is linearly independent. Basically what this means is one eigenvalue gets one eigenvector. Like the previous problem we had, the eigenvector, or the eigenvalue 2 had two different eigenvectors. So theorem 2 does not apply there. You have to have distinct eigenvalues with distinct eigenvectors. So you have that one-to-one correspondence between them. And so with that, we've done the intro to eigenvectors and eigenvalues. Next time, we're going to look at how do I find an eigenvalue when you're not given anything but the matrix. So we'll do that next time. So y'all have a good day, and I'll see you in the next one. And of course, keep the annotations.